Hello. In this video, we will study several calculus notions in terms of parametric equations. We're used to using regular Cartesian equations, or functions of the form y equals some function of x. Here we're using h instead of the familiar f of x. The letter name does not matter. We're used to doing calculus operations with functions of this sort. We do derivatives and integrals and find arc lengths. We'd like to see how to do those same sorts of things when the function is expressed in terms of parametric equations. First of all, let's talk about derivatives. To find the derivative of some function defined in terms of x, we denote that y prime, or h prime of x, or dy dx. Let's think of this with parametric equations. I'm going to imagine dividing both the numerator and the denominator by dt. And I realize this is skipping some steps here. This is a little bit hand-wavy, but the notion should be straightforward and it should give us an intuitive understanding of this formula. We get dy dt divided by dx dt. In other words, if we have two parametric equations where x and y are both defined in terms of t, then we can find the rate of change of y with respect to x. We can find y prime simply by doing the derivative of the y function divided by the derivative of the x function. Or we could state this as we did just now, dy dt divided by dx dt. Once again, this is not a rigorous proof, but it should give us an intuitive understanding of this derivative when we have parametric equations. Let's talk about integrals. The typical way to think of an integral is to think of it as representing the area under a curve. If we have some function y equals h of x, then the integral from a to b of h of x is the area under that curve. How can we do this in parametric equations? Well, in parametric equations, we have a parameter t, and the t value need not be x or y. So let's think of the start of this curve where we start taking area. That's some value of the parameter. Let's call it alpha. And then the end value, let's call this t equal to beta. So as the parameter t ranges from alpha to beta, this curve is sketched out. It's important that as t ranges from alpha to beta, the curve is sketched out exactly one time. Another way that we could write this integral is the integral from a to b of y dx. Now, once again, our derivation will be a little bit hand-wavy, but let's think of how to do this in parametric equations. Y was the function g of t, x was the function f of t. So if we take our integral from a to b of y dx, let's replace the y with g of t. Next, let's think about dx. If I take dx and write dx dt, that's the same as f prime of t. That's the derivative of the x function with respect to t. I can rearrange this notation and solve for dx. dx equals f prime of t times dt. So if I substitute f prime of t dt in for dx, I will have an integral in terms of t. I replace the dx with f prime of t dt. This integral is all in terms of the variable t. And as x ranges from a to b, t ranges from alpha to beta. So this expression gives us the area under a curve. Once again, we're being a little bit sloppy with how we handle the notation, but the intuitive idea should make sense from this. Let's talk about arc length. When we did arc lengths in Cartesian expressions, where y was a function of x, we had the following formula. Let's think about how we derived this formula. Here's a curve from a to b, and let's think once again that the parameter t ranges from alpha to beta in order to sketch out this curve. If we focus on one small portion of the curve, we can think of a small length of the curve as being approximately equal to a straight line. The x distance is a small change in x that we call dx, the y distance a small change in y that we call dy. So in order to find this length dl, we can use Pythagorean's theorem. dl equals the square root of dx squared plus dy squared. If we divide everything by dt, then in order to simplify the square root, we could bring the dt in. Outside the root, it's just dt. To bring it inside the root, we square it, dt squared. To simplify, we have the square root of dx over dt squared plus dy over dt squared. These are the derivatives of the parametric equations. If we solve this expression for dl, that's multiplying dt by both sides. So we have dl equals the square root of dx over dt squared plus dy over dt squared. And then multiplying both sides by dt, we have a dt at the end. In terms of parametric equations, this is our expression for dl. So to find arc length, L, we take the integral of dl, and we just found in terms of parametric equations that dl is the square root of the derivative of the x function squared plus the derivative of the y function squared dt, where the parameter t ranges from alpha to beta. We can also find surface area of a rotated solid in terms of parametric equations. Once again, we have an x equation, x equals f of t, y equation, y equals g of t. And for this example, let's just think of rotating around the x-axis. We could also rotate around the y-axis and get a similar sort of a formula. Well, surface area, if we rotate around the y-axis, it's the integral of 2 pi, and the y is now g of t. And then we have dl, which, just like before, dl is the square root of the derivative of the x function squared plus the derivative of the y function squared dt. This ranges from alpha to beta, where the start of the curve is when the parameter equals alpha, the end of the curve is where the parameter equals beta, and the curve is sketched out exactly one time as t ranges from alpha to beta.